A motorboat maintained a constant speed of 24 miles an hour relative to the water in going 35 miles upstream and then returning. The total time for the trip was 3 hours, and we want to find the speed of the current. Uniform motion problems can be organized using a 2x3 box. The rows of the box are going to be used to describe trip 1 and trip 2, but since we're going upstream and downstream, those would be better row headers. It's good to have meaningful labels. It helps us to remember what goes where. The column headers want to be something such that we can multiply the first two columns together to get the third. And in uniform motion problems, that's going to be this formula for determining the distance. We're going to multiply rate times time in order to come up with the total distance being traveled. Now let's head back into the problem and see if we can figure out what goes where in our table. A motorboat maintains a constant speed of 24 miles an hour relative to the water. Let's recall that we want this rate to be the ground speed, or the speed relative to the ground. The ground speed is the true speed of the boat. It's how fast the boat really is traveling, and that's taking into consideration the effect that the current has on the speed. The speed relative to the water would be the speed in still water. But that's not how fast the boat is actually traveling. So we're looking for the true speed, and we don't have that information just yet. Let's look a little further in our problem, and we see that we're going 35 miles upstream, and then we're going to return that same distance. So we traveled 35 miles upstream, then turn around and travel the same distance of 35 miles downstream. We're told the total time of the trip was 3 hours, but we're not sure what goes into the time upstream and downstream. There's certainly different times. So since that's not clear just yet, let's keep moving through and see if we can figure out something else. Notice we're being asked to find the speed of the current, and when we're being asked to find a quantity, that is our unknown, and we'll assign x to that value. So when we solve our equation, we'll solve for x, and that'll give us the quantity that we've been asked to find. Since we don't have much of our table filled in, let's think about this concept drawing to hopefully help us understand more about what goes where. So we're in a boat, we're traveling 35 miles upstream, and then we're going to turn around and travel the same distance back. We were told that the boat has a constant speed of 24 miles per hour relative to the water. So we can say down here that the boat speed is equal to 24 miles an hour. Essentially, that's what the speedometer reading in the boat would say. It's how fast the boat would be traveling if there were no current. The speed of the current was the unknown quantity, and we let x represent that value. So let's say down here that x is equal to the speed of the current. Let's say that the current is moving in this direction. So when we're traveling against the current, that's when we're traveling upstream. So the ground speed for the trip upstream is going to be the speed of the boat minus the current. Notice that it has to be 24 minus x and not x minus 24 because the boat must be traveling faster than the current. In order for us to progress upstream, the boat has to be going faster. If the current was bigger, we would be pushed backwards. So it has to be boat speed minus current speed. Then our boat turns around and travels 35 miles downstream. When we're traveling downstream, we're traveling in the same direction as the current. And so the ground speed here, or the actual speed, is going to be the 24 miles an hour speed of the boat plus the speed of the current. The current is assisting us as we go downstream and causing our rate to be faster. Now this problem is different than some of the others that we've seen because we do have two columns populated, but it's not the first two columns. This time it's the first and the third column. But we really only need two columns to be populated in order to be able to figure out what the third column must be populated with. If it was the first two columns populated, we would be multiplying across to come up with the third. In this case, we take the 35 and we're going to divide it by the 24 minus x to get the center column that's going to be 35 divided by 24 minus x. And as you can see, if we were to multiply the first two columns together now, we would get the third. So again, in order to get the center column, we're going to take the 35 and divide it by 24 plus x to get 35 divided by 24 plus x in the center column. Another way we can think about that is if we look at the distance is equal to rate times time formula, and if we solve this for time, we would do that by dividing both sides by the rate, and we would get that time is equal to the distance divided by the rate. So what we had in this particular case was a quantity in the rate column and a quantity in the distance column, and we needed to figure out how to represent the time in terms of distance and rate. And we got to that by simply dividing the distance by the rate. So now that our table is populated, we're ready to try to set up an equation for us to solve. The piece of information that we haven't used yet is that the total time for the trip is 3 hours. So that means the time that it took us to travel upstream plus the time that it took us to travel downstream is going to be equal to a total of 3 hours. Well, this is the time that it took us to travel upstream, and this is the time that it took us to travel downstream. So we can add these two quantities together, and their total should be 3. So we have 35 divided by 24 minus x, which is the time to travel upstream, added to 35 divided by 24 plus x, which is the time to travel downstream, and those two times need to add up together to be 3. Let's notice that the equation that we've created is rational. This is rational because we have the variable x in the denominator of a fraction. In order to solve a rational equation, we're going to multiply both sides by the LCD, which is the least common denominator over the entire equation. In this case, the LCD is 24 minus x times 24 plus x. So we multiply both sides of this rational equation by that LCD, 24 minus x times 24 plus x, and this is going to be written over 1. So let's now distribute this LCD into the first term. So we're going to have 35 divided by 24 minus x multiplied by our LCD, 24 minus x times 24 plus x, over 1. And then we multiply the LCD times this next term, so we're going to have plus 35 over 24 plus x times the LCD, which is 24 minus x times 24 plus x, over 1 again. And then we distribute the LCD into the right side of the equation. So we'll have 3 times that LCD, which is 24 minus x times 24 plus x. And since there were no fractions in this bit, I'm just going to leave off the over 1s. Now it's time to multiply these terms together to determine what their product is. So 24 minus x's are going to cancel, and we'll be left with the 35 in the top times 24 plus x here. So we have 35 times 24 plus x. For this second product, the 24 plus x's cancel, and what remains is the 35 times 24 minus x. And on the right-hand side here, nothing cancels. So we'll just copy paste for now and then work towards simplifying here in our next step. So this is where we are with our equation now. Notice there are no more fractions because multiplying through by the LCD cleared the fractions. But what we have is a quadratic equation. And anytime we notice that we have a quadratic equation, our first step is going to be to set it equal to 0 and then decide which of the 4 methods we're going to use to solve it. After it's set to 0, we can determine whether or not it factors. We might be able to use the square root method. Completing the square is always a possibility. This one always works. And so does the quadratic formula. So since we've noticed that it's quadratic, the first thing that we're going to do is set this entire thing equal to 0 and then decide which of these methods we're going to use. So to set it equal to 0, we need to distribute this and multiply everything out. So we start with 35 times 24, which is 840 plus 35x, plus another 840 minus 35x is equal to, let's hold on to this 3 for a moment and just multiply these two quantities together. Notice that they are the difference of squares in its factored form. So what we can say here is that 24 squared is 576 minus the x squared quantity, right? Now we're ready to distribute in this 3. Let's also simplify the left-hand side, noticing that we have these 35x's that cancel and that we can combine these 840s. 840 plus 840 is 1680, and 3 multiplied by 576 is 1728. And then we'll also distribute the 3 into the x squared to get minus 3x squared. From here now I'm changing my mind about setting it equal to 0 because I can see that we're actually going to be able to use the square root method. which means that I want to isolate the quantity squared in order to be able to take the square root of both sides. So my next step is actually going to be to subtract 1728 from both sides. So this is going to leave negative 48 on the left and negative 3x squared on the right. Now we can divide both sides by negative 3. I'm also going to switch sides here to say that x squared is equal to positive 16. And now we can take the square root of both sides. When I take the square root of both sides, it comes along with a plus minus, and that plus minus needs to go on the constant side. So now we have x is equal to plus or minus 4. This has been a long problem, so we kind of need to remind ourselves, what did this x value represent? Remember, back up here we said that x represented the speed of the current. And what we found was plus or minus 4. So we're going to ditch the negative one because that doesn't make any sense when we talk about the speed of the current. So our final answer is going to be 4 with the units of miles per hour, again just using the positive solution, and this was the speed of the current.